This is a presentation about how to investigate UI freezes. And one important detail is that I will tell you how to investigate them, not how to fix them. But I'll try my best to give some advices what to actually do with this problem of our IDEs. A little about me. I am software developer in IntelliJ Platform. I work on our threading model and concurrency and coroutines, all that stuff currently. But let's dive into the presentation. So to understand why do we have freezes in regular IDE or in the plugin, we need to understand the architecture of IntelliJ Platform. So you could notice that our IDEs are UI applications. And as regular UI applications, they have UI framework. Our UI framework is based on top of Java AWT. And also, as a way to work with our model, kind of structures that contain data about users' code, we use read-write logs. Yeah, and recently, for the last maybe 5 years, we started adopting Kotlin coroutines, which need to be integrated nicely into both these concepts. Yeah, so let's talk about consequences of building an application on top of AWT. So we have a dedicated single UI thread, which is called the EDT or the event dispatch thread. And this is basically a thread where all interaction with the screen works in simple terms. Basically, all painting requests are performed as events on EDT. Yes, it is called event dispatch thread because it runs events. Should be pretty obvious now. Also, all interactions with Swing, UI framework, which is built on top of AWT and is a bit higher level, they also happen on EDT. And there is one important thing is that anyone basically can submit their code for execution on EDT. That's free. That approach follows Swing standards and practices. You just hit Swing utils invoke later, and then you can run arbitrary thing on EDT, and you can do whatever you want. Like you can access files, or you can simply run an infinite loop, and it will freeze the IDE. That's about EDT. Well, we also have read-write log. We had it from the very beginning, from 25 years ago, and our IDEs are we rely on this model of having the read-write log. So first of all, why do we need it? We have several structures that basically a mutable shared state, and we need to ensure exclusive access to them. Such structures include PSI, which is our representation of syntax trees, VFS, which is our representation of file system, indexes, project model. Well, project model is how we understand the build system that is used to import a project. As about the API, we have basically two methods. There are plenty of flavors for these two methods, but basically we have read actions and write actions. And basically, if we have read-write log, then read actions allow executing some code inside read log, and write actions allow to do the same under write log. We use read-write log, and it means that we can read the same mutable shared structures in parallel, but we want to ensure that only one thread writes them. So write logs are mutually exclusive with everything else. Yeah, as we were writing the code, the acquisition of read and write logs was usually proceeded in blocking way. So the thread that wants to acquire a log gets blocked, like in thread park way. Or with coroutines, it gets suspended, which is slightly nicer, yes. Yeah, so there is an important thing about IntelliJ Platform is that write actions can run only on EDT. There are lots of reasons for this behavior. It makes writing the code very convenient, writing the plugins, I mean, for our IDE, because your UI thread is only consistent state of data structures. But it has also lots of disadvantages, like it should seem logical that write actions should not run on EDT, right? But unfortunately they do. Here I need to say that we are aware of this problem and we know that it's a problem. We are working on it, but it's not that easy to fix 25-year-old code base. So we're getting there, actually. So yeah, the bad consequences of write actions on EDT is that they freeze UI because they're just a code that does not allow to paint anything. For example, you could have seen the following modal dialog. Well, this particular dialog just is a little bit fake. It looks like a modal dialog, but in fact, it is a long write action. And that's why you cannot cancel it. You cannot do anything with it. Yeah, it is animated, but that's because we have some tricks to run animation while write action proceeds. But yeah, the sad thing here is that it's you as a plugin developer can actually do nothing with this. This is a platform problem, but we're working on it. Another less obvious case of why we have UI freezes is that read action on background can actually freeze UI. That sounds strange, but let's dive into this example. So let's use the following two diagrams for expressing threads. So on top we have EDT, and in the bottom we have some background thread, and we have a timeline which goes from left to right. So imagine that we have a background thread that runs some long read action. Completely normal stuff, right? Background threads want to sometimes read PSI for their purposes. Meanwhile, the EDT does some painting. That's also totally normal behavior of EDT, but then EDT wants to run a write action. And you cannot actually predict where it happens. I mean, usually write actions are consequence of user actions, but sometimes the platform decides to just fire write action randomly after a certain timeline delay, after a certain timeout, I meant. Yeah, and because this is EDT, and we need usually to start this write action like right now, we cannot postpone it. This write action blocks EDT. And we cannot run some other painting events because they might rely on the result of this write action. And basically, we have this situation where a read action on the background causes a UI freeze. Yeah, and after some time, read action stops, and then our write action proceeds doing whatever it wanted to do. But we had a freeze, unfortunately, in this case. So let's figure out how to investigate such scenarios, or maybe something more. At least if we understand how to where to look into IntelliJ diagnostic data, it might prove useful in other sorts of UI freezes. So basically, investigations should start with opening a thread dump. IntelliJ creates a thread dump on plenty of actions. When you have a UI freeze, there will likely be a freeze dump, and you will probably get somehow notified about it. You can capture a thread dump manually with JStack. But let's assume that you actually have a thread dump. The problem is that it can be quite huge. For example, this is only one thread. Personally, I get it looks scary. It's a lot of text, and this is just a thread dump of EDT, and we have like 100 of other threads, which are also doing some non-trivial work. And also we have coroutine dumps, which I will cover a bit later. But yeah, I get that it might be intimidating. So let's look at where should we look in this mess. So we have a UI freeze, right? It means that EDT cannot paint whatever it wants to paint, or process user events if it needs to. Well, let's search for EDT. It is in our thread dumps. It's called AWT event Q0. And in the vast majority of cases, it is blocked on the read-write log, the one that's used to protect our shared data structure. This is the most frequent source of our UI freezes. There are others, but that's the most popular one. So that's a bit shortened example of a thread dump of a thread dump that is narrowed to one thread, to EDT. It also contains lots of symbols. So first of all, we have the name of the thread. It is indeed EDT. You probably found it already with a text search. Then we see that it is blocked. Thread state could be waiting, blocked, timed waiting if the thread is blocked on thread sleep. Here we see that it's blocked on monitor because it is java-lang object.wait0. And if we scroll in a little bit lower, we could find the phrase run write action. Basically, the next step after you found a thread that you're interested in is to search for these magical strings like run write action or run read action. They will tell you about what the IDE tries to run. Like here, it tries to run write action for whatever reason, and it cannot acquire the write action, which means let's think why the IDT cannot run write action. That's because there is some alive read action somewhere in a background thread. That's most often the case. So next, we need to search for this redaction. And here we can look for redaction in this thread dump. Most likely it will show us a thread which basically runs that redaction. Here it is. I took it from our random thread dump with a freeze. So this is a background thread. This particular thread was taken from coroutines. This is a thread from coroutine thread pool. We see that it actually does some non-trivial work. It does something connected to serialization in Java. In VFS, basically, this persistent FS3 accessor is part of our virtual file system. But yeah, we see that there is a background thread that does non-trivial work, and it is redaction. Which means that while this redaction runs, we experience a freeze in our IDE. And that's basically it. That's how to investigate it. Congratulations, you found out why your IDE is frozen. But to not make this talk so useless, I'll actually tell about ways of resolving long redactions. So the best advice I could get, and that works in majority of cases, is to use non-blocking redactions. Let's figure out what it is. So let's recall our previous teaching diagram with two threads, EDT and the background thread, where write action blocked while read action runs. Well, here we can notice that EDT wants to run a write action, and it wants to run it fast because we want EDT to be done with this write action and continue doing some useful work. So this read action that runs on background and blocks write action is called blocking in our terminology. But there is an alternative. So imagine that there is some ongoing read action in a background thread. And EDT does some painting or some interaction with the UI. Then the EDT in its next event wants to start a write action. We, as IntelliJ Platform, understand that write action is about to start, and we give a signal to the running redaction that it needs to finish. Then this reduction transitions into a special canceling state where it continues to run, but on the next call of progress manager.checkCancelled, it throws a special kind of exception that aborts its execution. Well, when this reduction reaches the cancellation point, it means that reduction is done. It is not done gracefully, but there is no reduction now. Nothing holds read lock, and we can start doing our write action. So write action can run. Meanwhile, this read action gets blocked if it wanted to execute like synchronously on this background thread, or it gets just kinda suspended and gets stored into a queue, and then it gets rescheduled once the write action is done. But effectively, this read action is blocked. So once write action is done, the ADT can continue doing other work, like it can process other user events or do painting. And this redaction, it now knows, because the platform signals it, that the write action is done and it can be restarted. And that's a very important point, that this read action is restarted from scratch. Like it gets aborted, and then the logic that was previously executing, it starts running again. Yeah, that's an important point. I'd like to reiterate it here. There is a mathematical property that's called idempotence, which means that if you execute a function several times, then it results, its subsequent execution does not affect some global state. And it's important to know that non-blocking reductions, reduction that conforms this scenario is called non-blocking. So such reductions need to be idempotent. It means that if you want to run a HTTP request, if you want to fire HTTP request from a non-blocking reductions, you need to think twice, because your request can be actually resent several times, because redaction can be aborted. And like I said, in our code, the cancellation points is a calls to progress manager check cancelled, which throws a special exception, and that's why, and that's how redaction gets aborted. So while in this blue segment, after the first redaction, the redaction continues running until it reaches the check cancelled. And basically, if you don't have any check cancels in your redaction, then you have kind of a blocking redaction, because the write action cannot start for the whole duration of redaction. Yeah, that was the first advice. In our API, it's called redaction.nonblocking. That's a Java-friendly version of running non-blocking redactions. And yeah, another advice is to place progress manager check cancel frequently enough. Like the platform calls a lot of plugin code under redaction, under already provided redaction, and to behave nicely, the plugins need to call check cancel it frequently enough so that the outer redactions can be canceled. All right, let's switch to coroutines and how they fit into this perhaps convoluted picture. Right, so our coroutine API has functions like read actions, EDT write actions, and read it EDT write actions. First, you could ask, why do we need this weird name? Why it is EDT write action, not just write action? Well, the reason is that because we are on the way of introducing background write actions. I think in 2025.3, these functions are stable. It's called background write action, but it might not work that smoothly with everything else. Read and EDT write action is a function that helps to do a very specific pattern. So imagine that you need to compute something in read action and then apply this result in a write action. There is an API for this in our redaction.nonblocking builder, Java builder, and this is a coroutine version. And redaction, well, it's redaction, but there is a twist. Redaction in coroutine world is always non-blocking. That's because we started using non-blocking reductions in our platform. We saw that they work very nice, and we made them a default option of executing code under reduction in coroutine world. All right. So yeah, one important point about reductions is that they are suspending functions, but they accept a non-suspend lambda. This action as a parameter inside the reduction is non-suspending. That might be inconvenient because, I mean, we want to you could want to have suspends everywhere, but we want to keep actions short, and not having a suspend modifier does not allow you to suspend inside, and it is much more difficult to do some long task. Like in Kotlin, the API for sending some web request is in the vast majority of cases suspending, because it's Kotlin, everything is suspending, and we want to avoid that someone tries to someone tries to send a web request inside the redaction. That's why there is no suspend, just to avoid these things. Yeah, and also it's important to remember that this lambda can be executed multiple times inside the single redaction, because write action can cancel it. Let's proceed. Yeah, so coroutines are nice, but they introduce additional level of complexity, and we need to investigate issues in coroutines. I'll be honest, it is harder than doing the same in plain Java, and we have plenty of diagnostic tools for investigating coroutines. One particularly useful is coroutine dumps. Basically, every time you get a thread dump from our IDE with JStack, or when IDE captures a thread dump itself, the thread dumps also include coroutine dumps. That's kind of a state of coroutine tree at the moment of capturing the thread dump. So coroutine dumps look scary, they look unfamiliar, there's a lot of information, and you also need to know what to look for in them. So let's look at what we can find in coroutine dumps. That's an example from from the same thread dump I used before, but that's a part of coroutine dumps. Oh wait, no, not really. That's actually a thread. We'll come to coroutine later. Yeah, so that's some other thread from that coroutine dump. Yeah, we see again that this is a background thread, and it is blocked. And one interesting thing here is that it is blocked on run blocking. So run blocking is a special function in Kotlin coroutines library that allows you to call coroutines from blocking code without suspense, and then wait until these coroutines finish to execute. Naturally, the thread that calls run blocking gets blocked until all the coroutines inside finish. And here we see this run blocking. So our thread dump actually has an identifier of this blocked, of this run blocking. We can search for this identifier in coroutine dumps and find this snippet of code. Yeah, so here we see this is taken from coroutine dumps, and we see it is the same identifier, 32E180. You can check it, it's the same. So it's the same run blocking that matches that thread. And we can now investigate what's this thread doing and why it cannot finish. So we see that this coroutine is suspended. It means that it's waiting for something. It is stored in some queue. We can see coroutine context that's associated with this coroutine. From this particular snippet, we see that it runs on a dispatcher's IO scheduler that's limited to 11 threads. And yeah, these coroutines are taken from our scanning process. It is visible here. And we have this X8 off. It's kind of a deduplication of identical coroutines. It means that we have 8 identical coroutines that are suspended on something. But what are they suspended on? We see here that they are suspended on a read action. It means that this coroutine wants to run a suspending read action, but it cannot because there is because the write action wants to start. Yeah, that's a very nice property of IntelliJ Platform. When write action wants to start, it does not allow read actions to actually even start. So they wouldn't even prevent write actions from proceeding as fast as it can. Yeah, that was a small guide on how to look at coroutine dumps and not be that scared. In conclusion, what do you need to remember after this talk? So use non-blocking redactions. They are nice, but you also need to keep them short enough so that they don't want to so they wouldn't take lots of CPU and the restart wouldn't be that bad. But they are actually better than regular blocking redactions. Yeah, you also need to use check cancel frequently enough to help IntelliJ Platform being responsive. And yeah, I understand that thread dumps are scary and coroutine dumps even more. So, but once you get a little comfortable with them, they contain lots of useful information and they help you to introspect the state of IDE and figure out what's your plugin doing. So it might worth some time to invest into understanding these formats. That's it, basically. Thank you for your attention.
Great talk. Thank you very much. Someone in the chat already said this should be put up on the docs, the SDK docs.
I think it already is.
This talk? I mean, the whole talk, actually.
The whole talk.
Anyway, thank you very much. I'm a .NET guy, so for me this looks a little bit less scary now. Good job on that. We do have a couple of questions. So one question that I actually also understand is, that's why I'm gonna pick this. What is the process of deciding when you call, and how is this call exactly called? Progress manager.check cancelled to kind of, you know, have the help with the maximum responsiveness of EDT?
Well, basically, the platform has already strategically placed check cancels in important places, like when you call platform functions, like when you request a service, you transfer control to the platform, and the platform already has check cancels there. So if you call check cancel inside, if you retrieve a service inside a redirection, most likely you are fine. Here, the platform will check it for you. But sometimes you, in your plugin, do some non-trivial work, like you have recursion or you have loops where you iterate over long lists, and that can introduce problems in cancellation. So my advice is that if you have long loops, it might be nice to insert check cancel there. There is one pitfall though. Check cancel, unfortunately, it is not free. So you need to insert it with some debounds, like check cancellation once in 100 iterations, so that it wouldn't be visible in profiles or it wouldn't harm performance, but still give you enough responsiveness so that reduction gets aborted promptly.
Mm-hmm. So I think sorry, just to follow up. So one question would be, so where I use it is when I do heavy work on the PSI, right? I have a visitor who has to go through a lot of structure and recursively. Yep. So can you say something about so what's actually done in check cancelled? How heavy is the function call? Roughly, I don't need an exact answer, but just an estimate. So if it's just a quick call that takes nothing. I can place it anywhere, right? But maybe I want to consider it every 2,000 iterations or strategically placed, as you said.
So with this particular example, with the recursive visitor, there are already check cancellates in the platform. Like when before the platform calls your visitor method, it checks cancellation and it does it when it needs to do so. About how heavy check cancelled and what can be so heavy inside it. To be honest, in Progress Manager check cancellated, there is a bit heavy logic with tracking of threads that run under progress indicators. That's kind of an old class, a legacy class for managing cancellation and progress reporting. So yeah, there is some heavy stuff like threads get stored to concurrent hash maps. These hash maps can get resized at some random points. There are some synchronized. There is a bit lighter version, cancellation.checkCancelled. It should also work, but not with progress indicators, and it is much lighter. But generally, I think you would be fine if you use Progress Manager check-cancelled. I mean, having cancellation, even that slow, is much better than not having it at all.
Yeah, I know. We got a question in chat. Put it on.
I asked that question because it could come from me.
Right.
So why write actions have to be executed on the EDT? EDT. T is already for thread, right? Yeah. See, not Java.
It was just decided on the very beginning of IntelliJ idea that we will run write actions on EDT. It has advantages. It is more convenient to write such code, like when you have write actions only on EDT, when you have this invariant. First of all, you don't need to take a read log on EDT. If you want just to read your data, then you on EDT, then you can read it right away because you know nothing else can mutate this data in parallel. Second answer is that when you have this restriction, you can implement a much more performant version of log. So since 2016 up to 2022, we had a very performant log in IntelliJ Platform. It was really fast. What we have now is not that fast. But the old version worked only with this assumption that we have this restriction that write actions can run only on EDT. Now we are running some of write actions on background. Yeah, our current log is slower, but it allows us to actually run things on background. Third answer is that you don't need to care about consistency in your EDT. Because when you read data, it's always consistent. You know, nothing changed it. Yeah, but you can also ask, okay, it's bad. Actually, let's just run all write actions on background. Unfortunately, IntelliJ Platform is a very old code base. There are lots of assumptions, and there are lots of listeners, synchronous listeners inside these write actions. And these listeners do whatever they were allowed to do. For example, you can add the listener to some VFS, which will run inside the write action, and you can draw something on the screen in this listener. Nothing prevented you to do so, because write actions were running on EDT. It is naturally allowed. And that's the reason why we cannot just take all write actions and run them on EDT, because we have our own code and we have third-party plugin code which relies on this property, and it is lots of work to untangle EDT and write actions. But we are working on it.
All right, thank you. Clears things up. Another question? I would have one, definitely, okay, for my times when I deal with an IntelliJ platform. So beyond simple search, what advanced tools do you recommend for analyzing large thread and coroutine dumps to pinpoint root causes quickly, to ease the scariness even more?
Well, we have internal action, which is called analyze stack trace or thread dump. Basically, it takes whatever it is in your clipboard, whatever you copied now, and tries to parse it. It displays the thread dump in a nicer way, so you can navigate in actual frames, in actual stack frame into your source code. And also there is a built-in tool which is called freeze analyzer. So in some simple and understandable cases, it can even show you a thread where it says why this thread is a reason of a freeze and who to blame in it. Maybe it's platform, maybe it's something else. But yeah, it displays a human readable reason of a freeze. So yeah, the internal action analyze stack trace or thread dump. That's how it's called.
Okay, thank you. And one more question. Any of you two, Patrick or Jacob, wants to ask that?
Chris just pointed out that the check cancel doesn't seem to be on the threading docs page in the SDK docs. I didn't want to type. Yeah, we need to fix that. I didn't want to type and search myself, but I just take Chris's answer for granted. So we need to fix that. So we will take that into consideration.
Yep.
Yeah.
Cancellation token in .NET. Okay, I will just follow up with another question. Also sounds very interesting. So non-blocking read actions require idempotence. I never said that word. Just read. What are common pitfalls when converting existing blocking read actions to this non-blocking pattern?
Well, basically, I mean, non-blocking redirections are better than regular blocking redirections, but we could not just take and convert everything automatically in the platform, because the existing code sometimes relies on the computation not being run several times. I think that's the biggest pitfall. It's very important to remember that it is executed several times. I mean, it's fine in the majority of cases, like when you just find something in PSI hierarchy. But if you do something non-trivial, it is very unexpected behavior, then it runs several times. And that's why we have two separate kinds of reductions. Yeah, that's the biggest pitfall.
Okay, so individual to the specific actions, basically. Yeah, when they deal with PSI, then it's cheap, more or less. It comes automatically. Otherwise, you have to, consider what the action is actually doing.
Yeah.
Okay. I can see a last question here, but I have no idea. I cannot ask the question if I have no idea what it is about. So, question number 2. One of you, please.
Yeah. Okay. So, can you elaborate on the difference in how read action in coroutines and read action non-blocking handle cancellation and restarts?
Well, in coroutines, there is a slightly different way of managing cancellation. Actually, we reuse and extend, in some sense, the cancellation model from coroutines. So in coroutines, there is a kind of implicit all-present coroutine context. If you know Haskell a little, that's kind of a reader monad that's associated with your every computation, and there is a special thing that's called job in Kotlin coroutines. And every time you call a suspend function, this job is checked for cancellation, and if it is, it throws an exception. We reuse this in suspending redaction. So basically, when you run a suspending redaction, the job from coroutine context is taken, and it is kind of installed in the computation that runs under redaction. And we every progress manager.checkCancelled checks this job for cancellation. So it means that if something outside canceled your whole coroutine, then your redaction will also be canceled. There is very similar thing with non-blocking redaction, but because Java version of the same pattern. But it was old. It also respects progress indicators, so it's slightly more complicated. I think that's the difference. There are very, very subtle differences between them currently also, like the Java version of non-blocking redactions uses EDT to reschedule itself in case of cancellation, and suspending redaction does not. But I think it's more of a technical depth from my side, so it will be fixed. But I mean, the answer is that ideally they are the same, and basically you need to think of them as the same.
Okay, one more.
You have one more? Go ahead.
Well, about tooling that could help in analyzing thread dumps and coroutine dumps.
We got that already.
Yeah, it's action analyze
it's analyze. So I wasn't aware that analyze thread dump is an internal action. Maybe I always have internal action on.
But
so that's why.
Well, just a follow-up question to that one, actually.
Okay.
But any external tools? I think that EuroKit could help to some degree. EuroKit,
I am not actually sure to analyze. Not really. I mean, EuroKit is a tool for analyze profiles and heap dumps. For investigation of freezes, in the vast majority of cases, it is enough to use just a thread dump. I mean, I personally almost never use profiles, or I mean, there are very difficult freezes where I have to use heap dumps, but it's very rare, and it's enough just to use thread dumps.
Okay, so as mentioned before, mostly our internal tools.
Yep.